Hey everyone, this is Dave again, and at this time I'm impersonating Greg Dudek, and this is the October 5th lecture, number 11, on 2D arrays, which was again lost for some strange reason of the lecture recording system at McGill. So, Prabjot had just done the lectures on pointers, and the first thing that we wanted to cover in lecture 11 is a little bit more practice. So hopefully you might have messed around with pointers yourself because it's such a fun topic that who could want to do anything else with their weekend. But if not, here's some of the things which look a lot like what we're going to see on midterms. So it's good to go through this pointer exercise. We have two different sections. We have a section of character-like pointer access. Okay, up here, we're going to make some characters and some strings. We're going to use pointers to mess around with them. That's some of the things, looks a little bit like what I'd done a few weeks back. So we're able to access C strings with pointers. Hopefully that's not surprising by the time you get to this lecture. And change the values inside the strings, for example. And then here's some practice of the kind of things Prabjot was doing, which is to mess with also, I'm just going to move this guy really quick, mess with the integer type data, both single integers and arrays with pointers, and print the values of both of them out. So this time we have what's called box and arrow diagrams. That's a way which we want to think about how pointers work, rather than writing the addresses out every single time, like we were doing in the lecture 10 slides. We'll just hope you understand that there's going to be an address for everything, right? So over here, letter has some address, like last time we were talking about writing something like, this had 4D as its address, which is, it basically tells us where in memory is the slot, which is holding this little character B right now. And then an inside C pointer, really, there was, inside here it said 4D. That's not the address, but now the value of the pointer. And of course the pointer takes some memory, like, it can be 5D. Again, these are hex numbers, which just represent addresses, right? They'll be much longer than this in your real memory. Okay, but so this time I'm not going to show any of that stuff. We're going to talk about box and arrow diagrams. The arrow always indicates that the pointer holds the address of the memory which the arrow is pointing to, right? So it's a more graphical representation, and that's usually what you want to visualize when you're working with pointers. We're doing the midterm exam. If you want to, you can also write out the address of each particular memory. Both works, but it's a little bit faster to do the box and arrows. Here's the box and arrows of our little char examples. We have the letter variable, it holds B. We have a sentence that's an array of characters. The printable characters are ending with \0, which we don't see here, but we get for free because we have the double quoted string in C. It always gives you \0 in the perfect spot. We make two pointers, CPTR1, which is a char pointer, and it takes the address of letter, right? So that's like what I drew, such as 4D. It holds that address. And then CPTR2, we don't have to say address of sentence because arrays are this special thing in C which sort of give up their address for free when we just say equals. It turns out to be fine to write address of sentence also, and that would work just fine. So both ways are okay. However, most commonly we don't write the address of because it's more writing that we don't need to do, and so why? Right, so skip that. And now we can modify the data inside sentence with array syntax. Sentence 3 equals I, so it's going to be 0, 1, 2, 3, right? That will change to I. And we can equivalently do CPTR2 equals. So CPR2 is going to be 0, 1, it's going to be the W box, and equals now the dereference operator. We also called the get values at address operator. of CPTR1. That means follow this arrow, grab what's there. That's a B. So stick the B here, and hopefully you got it if you went through that example yourself. So 2 birds, right, is the final result. Both of those ways are sort of equivalent to change the data now. So pointers work, they're useful, and that's the kind of thing you're going to do in real C programs with them, right? Not in toy examples like this, but if in places where we really want to walk through the array and then change different values, that's what pointers are for. So hopefully it's starting to feel more comfortable. Make sure it is. If not, let's do more practice. Come to office hours, right? Here's the memory representation. These numbers, 24 and 32, are, I think, correct. If you think that the memory starts at 0, it goes up till 7, if I count correctly. 0, 1, 2, 3, 4, 5, 6, 7. So then we have 8, 16, 24 is where letter is located at, right? That's the B, and 32 is the beginning of sentence, right? So that's supposed to tell you, something like this is happening in memory, and you can also use this picture if you'd like, right? And that all works fine. And so then things like CPTR with 2, CPTR2 with 2, it takes 32 and it looks it adds 2, right? So CPTR 2 that's accessing memory at spot 34, and we could also just count forward 32, 33, 34. What box is that? The W, right? So everything makes sense. As long as you know how the tools work, you can reason about everything that's happening, okay? And hopefully you could get through this type of example by now. And other little modifications, right? It's a good thing to ask yourself, what would happen if I change this value? Or what happens, for example, what is it possible to do CPTR1 on the left side equals, what are the kind of things that I could write on the right side, right? Well, it turns out I could write C. I could also write CPTR2 with some kind of indexing, like number character 5. I could also write sentence, let's say 0. All those things are good, and they all change the value of letter, okay? More practice on your own is a good idea, okay? Box and arrow diagrams for the integer problem. We have int number 42. That is what we're familiar with, I hope, by now, and that just creates a single new variable, which is integer type, holds 42. It's going to have some address for its memory. We're not using it yet till a couple lines lower. Int lotto picks, I don't know if these are statistically likely to win you $1 million, but maybe that's the whatever. It's just some random integers, 7 of them, enough space for 7 integers. Now, IPTR1, integer pointer 1, equals the address of number. It's the exact same story that works for characters. There's nothing different when you switch the type. It's only that we know that the data in the actual boxes represents now 4-byte integers, as opposed to 1-byte characters, which are supposed to hold text strings. Okay, so just the underlying type changed, but the mechanism, how we make pointers, what's going on here with addresses is all the same. Again, IPTR2 is an int pointer which can point to an array without the address of character, right? Because of the way arrays work. Int arrays also work that way, so all is good. Lotto picks 3 equals number. Lotto picks 3 is going to be 0, 1, 2, 3. It's going to be 38. So that's pretty straightforward. Lotto picks 3 equals number should look like stuff we've been doing before, so that's going to be changed to 42 because the value of numbers is pretty straightforward. IPTR1 equals IPTR2 is not now changing the underlying values. because we haven't used the star operator anywhere on this line. So when we don't use the star operator, then pointers are simply addresses, and this means that we write a new address into IPTR1. And which address do we put? The one which IPTR2 is currently holding. We can tell that which one from our box and arrow diagram by looking at its arrow. It's pointing at the beginning of autopix, so the 8 value at the beginning of the array, and we're going to write that address into IPTR1. That means we're going to change where it points in the box and arrow picture, right? So whenever you assign a pointer to something else, that means the pointer points at that value on the right-hand side now, okay? Equivalently, it copies the address. So now we can use IPTR2 equals IPTR2 1, so we have 0, 1, that's the 18 slot, equals dereference or address of IPTR1. Now don't get confused because IPTR1 is pointing at the array right now. The dereference operator just says get me the memory at the address I'm holding, and C doesn't really keep track of whether that happens to be an array or not. It just gets the memory right where your arrow is pointing, so it's going to pull out an 8, the value 8. And this point here is important to think about. Star PTR is equivalent to PTR0. Well, what does PTR0 do? If we did that on this pointer, for example, it would say, get me the first entry in the array. Well, because the pointers happen to be pointing at the beginning of the array, that would also be equivalent to star PTR, because that says, get me where I'm pointed right now. If I'm pointed at the beginning of the array, then getting the beginning of the array with indexing 0, both the same thing, right? And it turns out that we have two equivalent ways to basically index into arrays. Star PTR plus I in brackets is the same as PTR in square brackets I. You might want to think that through a little bit yourself, but hopefully the box and arrow way of thinking about things makes that not too scary. Both plus I and this I just mean move forward a certain number of boxes inside the array, and both of these things get you the value at those things. Just to complete this one, here we were replacing the value 18 with 8. Okay, that next slide just shows you hopefully what I told you happens. I hope I didn't make any mistake, but I think that we're all clear here. Okay, so practice more. It's good for midterms. It's coming up in assignment 3, and I hope you are getting the hang of pointers by now. But we'll just keep at it. So lots more practice coming on, and hopefully it gets to the point where it should feel natural and not too scary, and then you're a strong C systems programmer. Okay. And so for the rest of this lecture, we're moving on to the next topic, which is 2D, working with data which has a 2D layout. The reason to work with this kind of data is that a lot of real software systems represent 2D data, like this image from a video game. Of course, if you take a picture with your camera, satellite maps, you're taking Google Maps, you say, I want to know how to get from my home to McGill, and you want to look at the satellite imagery, right? That's or a weather map. All those things are 2D. It's important that we can represent those things in our data structures, and we're going to be doing image processing in assignment 3, and so we're going to show you at this time how to deal with 2D arrays in C with a couple of the different data structures that are involved. So the two things that we're going to cover during this set of slides is 2D arrays, which have fixed size, things like a tic-tac-toe board that's always 3 by 3, and arrays of pointers which have more flexible size, such as the argv that you get passed into your program. When the user calls a.out with a list of words, all the words can be different length. And so one is fixed size, one is more flexible, and they have different kind of pros and cons. Greg got only sort of to the end of the 2D array section, and so I'm going to stop there, and then the lecture from I believe the date is then October 10th, is where I picked up in the actual lecture hall, continuing on. So that's our goal for this little YouTube video. We're going to try to get through the 2D array section. So that's right, this example. Okay. 2D arrays are declared by putting or by repeating the size syntax. So the first number in square brackets was a 1D array, right? That meant to make memory for 3 boxes, right? Which could each store whatever type was here, like int. Okay, and now when we add the second one, right? So when we say another 3, that means that inside each one of these 3 boxes is another array of 3 boxes, right? So you can think of this nested format. Memory is only 1D in a computer, right? So all the address is we just use one address and it just increases. So there's not actually a 2D structure, but C is going to let us, think about the fact that, okay, wait, if I stacked the 3 rows inside here, here, and here, that would actually be a nice way to capture this picture. And so a 2D array is basically a convenience that C gives you and other languages give you to use this 1D memory in order to represent 2D things like images. So it's used a lot, and it's a nice feature. It makes programming more fun and convenient. And the underlying type, like int, means what's inside a single one of the boxes. All right. So every time you index into this array twice, then like for example with TTT 0 and 0, then what's going to be coming out at to be able to be used, to be able to set values and change values and use values, is the underlying type. So this example here is char. I shouldn't maybe have said int, but that maybe shows you that that you can have some variety. There's nothing special about char 2D arrays. You can also have int and float and every other type. Okay, but this one being character, so it could be, for example, a tic-tac-toe board, which you play X's and O's on, right? So all the array acts like a 1D array in some ways. You can index into it. It gives you values between 0 and the size -1. So if you say size 3, you can access values up to from 0 to 2. You can't move the array around. So TTT equals something else, or TTT plus are both syntax errors. So TTT equals TTT plus 1. No, bad, doesn't compile. TTT plus plus also doesn't compile. It's not a pointer, it's an array, and it has the same properties as 1D arrays, mostly, right? Except you have to index into it twice now. Okay, so we already gave away how to access the data. So once we've declared an array with n and m sizes, we can access the data with I and j from 0 to n-1 and 0 to m-1. Okay, and right, so 0, 0 is of course that box, and 2, 2 is that box, and we can either access the values just by writing them on the right-hand side, or anywhere in a C expression where we use a value, or we can set the values by putting them on the left-hand side of an equals, and then the right-hand side has to be a character. Why character? Because we declared TTT with the char type. And in C, then I comma j is not a thing, so that's also a syntax error. And some languages might allow that, but that's just knowing that's just how C works. So you have to use the square brackets twice. Okay, so it's not too tricky. Once you practice it a couple times, it should be fairly straightforward. You have to keep track of which size you gave in each spot, because you can't. If you're using the 2D array properly and not messing around, well, C lets you mess around a little bit. but if you're not, if you're keeping track of things in a sensible way, then you remember the sizes of your different indices, okay, and you don't exceed either one of them. So if I said n was 3, then I don't start indexing TTT 5 and then 0 or something like that, because I would have gone beyond the bounds, and then I can have seg faults if I do that, right? So it's just up to the programmer, just like a 1D array to keep track of the size. Now we have two sizes to keep track of. Use exactly the same tricks that you do for 1D arrays. Okay, so what are kind of use cases for 2D arrays that we see in programs all the time? When you have a couple of rows, 2 or more, and they all have the same length. So like here's the number of days per month in a leap year versus a non-leap year. Okay, we have February changes depending on leap year, and but there's always 12 months in a year. So even if someone invented 5 new kinds of years with maybe they want January to be shorter because we live in Montreal and it's also cold, right? So you could add another row, but all of these have to be length 12, the inside arrays, right? And that if you made it a third type. Not allowed that you have a different length in any one of the rows. Okay, so that'll bring up the next concept that's coming up. But if you have fixed length rows, which happens a lot, like years are always going to have 12 months, then 2D arrays are great, and they're very convenient, and you use them like this. And so, for example, when we're just storing data, like the grades for a whole class, then the variables can have meanings, right? Number of assignments, 5 we're having in Comp 206. Class size, 550 people. Well, this one is just 3 assignments and 2 assignments and a class size of 3. But we put variables in there and represent different sizes. It's just the fact that type of data has a fixed and reliable size, and so it's super sensible to use a 2D array, and we'll use those kind of things all the time, right? And more or less we're going to compare and contrast this with the next data structure that's coming up. Okay, what does it look like in memory? We have the box and arrow diagram for single pointers and single arrays. Here's the sort of array picture for a 2D array, like greetings, where we have 2 words. Each word has 3 letters or 3 characters. It has 2 printable letters and then a \0. Remember, we need our C strings to be 1 longer than the printable characters. So we basically start from the left to the right. We say, okay, this looks like an array of with 2 entries. Okay, and so we draw on the on this slide array with 2 boxes. It can hold 2 different things. It's just that instead of being something simple like a single character, then what we hold inside is now basically an array with 3 entries, right? So you end up getting something like this. I want to put one note. Greg during his lecture had said that it's important to remember that there might be a gap in between here. And he's both right and, he's right. Let's not argue with Greg. But it turns out that almost no modern compiler ever puts a gap there. And so actually there's lots of C code around that doesn't respect this fact. And so, it's a little bit goofy, but you can actually say things like char pointer, a single pointer equals greetings. And then you can, you need a name like P. And then you can do P++ and walk that thing through here, through here, through here. And then you say, okay, is it okay to do ++ again? So Greg's right, it's not strictly okay. It slightly violates the fact that the C is not exactly guaranteeing it, but this is one place where all compilers I've come across act nicely. So yes, you can just do ++ and keep going on. If somebody manages to find an example where that doesn't work, I would be interested in seeing it, because we have to keep track of what the compilers are doing. But so we can say, note, there's usually no padding. padding would mean, right, if there was any gap between the orange boxes, and that the plus plus of this pointer didn't move you on to the next entry, right? So in lecture I did say, okay, we have to think the fact that it might be padding, and that's what Greg also said, and that's strictly true. But in practice, but in theory there could be. So really, really safe C code wouldn't make this jump from this spot to this spot without the way that it would pick up this spot would be to say greetings 1, right? That's the beginning of the second box, and greetings 0 is the beginning of the first box. That's safe. That always works. And then once you do greetings 0 or greetings 1, right, then we can see greetings 1 and 0, and that's great. Always works, okay? And it turns out with all compilers, the other version works too, but that's why there's a little bit of confusion. If that hurts your head, you could just know that that kind of detail is not going to be on tests or so on, and not doing something like this, avoiding changing pointer types and just saying, okay, it's a 2D array, I'm going to stick with it being a 2D array. So pretend I don't know this is a possibility actually works pretty well, and you'll get far, and then you won't be confused, okay? So, but, in 206 we like to dig a little bit deeper, and so that's a little bit discussion which came up as well during the lecture with Greg, okay? What's undeniable is that the memory for this 2D thing doesn't change the underlying topology of your computer or something like that. So we have addresses which are increasing. So for example, we can have F1 for this box, and we're guaranteed that there's F2 for this box, and there's F3 for this box, and we're not exactly guaranteed over here, but a lot of times this is F4 and F5 and F6. Okay, so those are just increasing memory addresses. So you could say that the beginning of greetings 0 is F1, and also greetings 0, 0 is also F1. There's nothing special that happens at the beginning of these arrays, just like there's nothing special that happens at the beginning of a 1D array. And that's why we can say, char star PTR equals, word, which is a single array, and why we can also say char star equals greetings, right? We need a typecast for that second one. Good. So 2D arrays, we have the syntax. We know what they look like in memory. We often write it in this more convenient way, which is at the bottom here, because we want it to look like a 2D thing. And so now if I stack high on top of yo, I've accomplished sort of the way I want to think about having a 2D array, and because I have sort of these two indices, I can think of like an x-axis and a y-axis on an image, or in a big text file, or a grade spreadsheet or something, and I can index into greetings with greetings x, y, and life is good, and it's sensible to think about that and build your programs around that. We're just saying that it happens to be jammed into memory in 1D order by C, but it's perfectly reasonable to think about it being 2D like this, right? But the note is that it's only for your convenience and for your sensibility. And so if you just think, okay, there's still only really one address underlying everything, right? Okay. I don't know why we have to be so pedantic about that, but because it's the truth, so whatever reason, okay. And I think we're just about at the last slide where I had picked up in the lecture the motivation for the next topic, which is arrays of pointers. It says, okay, 2D arrays were great when we had a fixed size, when we had things like 12 months per year every single time. But what if I had a list of words, hi, yo, bonjour, hello? They're not all the same length, and for a 2D array we can only have only this size here, this size here. We don't have like a list of sizes, right? We want to say, okay, hi is 3, yo is 3, bonjour is something like 8, hello is 6. There's no place to put all those numbers, and so we're wasting space with the 2D array. It's basically this rectangular shape all the time. It has always the same number of entries per row, and you can't change that. So if you want to work with data that has varying sizes, like a lot of words in the dictionary, then you're looking for another data structure perhaps. You can also use a 2D array. You're just going to waste space. And I think that's the transition point. So I'll make this my last slide. Pick up in the October, again, I think it's 10th lecture for where I picked this up in class, and I continued on with arrays of pointers.